Thank you, Akash, for the introduction, and thanks also to the organizers for the invitation. It's a great pleasure to take part. It's my real first virtual full-blown conference, so it's an exciting experience. As Akash mentioned, I'm now based in Konstanz, but the results I'll show have all been obtained in Dresden or even at my place before in Munich. Okay, I'll essentially discuss non-local transport of spin of magnons, and I'm an experimentalist, so I like simple cartoons. The devices I'll be discussing look like this. We have a magnetic insulator, which can either be yttrium iron garnet that was already mentioned, or I'll also talk about this chromia, Cr2O3. And on top, we deposit platinum strips, 2 metal strips. And then we drive a charge current in one of the strips and generate this magnon spin current that we electrically detect in the second independent strip. I'll try to address 3 different flavors of these experiments. So this is the outline of the presentation. I'll first give a flavor of these experiments that we call magnon-mediated magnetoresistance, where you use spin Hall physics to generate and detect the spin currents. Then I'll switch to this chromia platinum heterostructures, where a spin superfluid phase has been reported. We tried to see that spin superfluid phase, and as a teaser, we didn't see anything, but I'll try to show you what we obtained. And then if time permits, I'll show results where we tried to really make sure that magnon spin transport really is in place. Okay, so let's dive into the results. I'll start with this magnon-mediated magnetoresistance. So again, this now is a cross-section. The bottom green thing is this magnetic insulator. I'm thinking of yttrium iron garnet, or YIG, in the following. And we have these 2 platinum strips on top. We drive a charge current, J sub C, here in one electrode, and then via the spin Hall effect, as introduced by Rembert, you generate this electronic spin accumulation at the interface, and that electronic spin accumulation then induces a magnon spin accumulation in the YIG. And these magnons shall be represented by these wiggly purple arrows here. And I'm not sure if you can see the shading, but the idea is that the magnons are generated only at this interface, and you get sort of a distribution, an accumulation of magnons around this generation electrode. And then if you place a second electrode, then these magnons will diffuse and eventually may reach the second electrode, and then the inverse process takes place. So the magnon spin gets converted into an electronic spin. That, via the inverse spin Hall effect, gives rise to a charge current, or we rather measure voltages, so open circuit voltages that reflect this non-local charge current here. And this is a magnetoresistance effect because the generation of the magnons and the detection is sensitive to the magnetization orientation. So if this large purple arrow here is the magnetization in the magnetic garnet, then the process I just described works well if the magnetization and this spin Hall spin accumulation direction S are collinear. But if you rotate the magnetization, then this process becomes less and less efficient until, for perpendicular configuration between the magnetization and the spin, you get 0 additional detectable effect. So this voltage or current that scales with this magnon-mediated resistance effect actually goes with a square of this angle, and the square of the spin Hall angle, the spin Hall generation efficiency. So you see sine square or cosine square type effects. I'd like to mention this once. What really got us going in that direction was a paper by Zhang and Zhang. And I'll show you in a second that actually the group of Bart van Vees, Ludo Cornelissen and co-workers really pioneered the field, and we were onto it, but somewhat slower. So this is a typical device. The top view, the dark gray thing here is the YIG, and these light gray things are platinum. For technical reasons, we originally also had some platinum, larger platinum contacts for the electron beam lithography, but what really matters is you should see 2 thin stripes of platinum, 2 thin gray wires, and you drive a current through, say, the left wire, and you detect the voltage in this independent right wire. And you try to see this non-local magnon-mediated magnetoresistance. And this works very well. We like to do experiments using magnetic fields of fixed magnitude and then rotating these magnetic fields in different planes in the interface plane or perpendicular to these interface planes. And if you can switch between magnetization and spin polarization perpendicular and parallel, then you see this cosine square or sine square modulation that I've been mentioning. And if you rotate the field in a plane where there's only this perpendicular configuration, you see zero signal. So this is the fingerprint in our perception of this non-local Magnon-mediated magnetoresistance effect. And then you can do these experiments playing with the gap between the two platinum contacts. And if you go from large gap, 1 micron, all the way to a couple hundred nanometer gaps, you see that the effect increases. And this is what the group of Varfa or Ludo has really done excessively. So this is a figure I took from this Nature Physics paper in 2015. And you see that this non-local resistance actually drops off with separation, with contact separation, but that the length scales are of micron size, and there is a more complex there's a more complex length dependence. So very interesting physics can be unraveled with these electrical experiments, and this is the key message of the first part. So really, in these non-local transport measurements, you can determine the Magnon diffusion length. Okay, and then we came across this article, which was published in 2018 by Yuan and co-workers, which reported a spin superfluid ground state in this chromia compound via non-local spin transport. That's, as I tried to illustrate, something that we can do. So that sounded very interesting. And in particular, we had access to high quality chromia platinum heterostructures fabricated by collaborators Tobias Kossup and Dennis Makarov at the Helmholtz-Zentrum Dresden-Rossendorf. So we decided to engage in these experiments, and this is the second part of the talk. Actually, you cannot measure this Magnon-mediated magnetoresistance in these structures, in particular because you need to go to low temperatures if you want to see the spin superfluid phase, and this Magnon-mediated magnetoresistance goes down with temperature. But what worked, as reported by Yuan et al., is to use the spin-Seebeck effect. So essentially what you do there, that also has been mentioned, the spin-Seebeck effect has been pioneered by Saito's group, Kenichi Uchida and co, about a decade ago. And you just replace the electrical drive by a thermal drive. So you now apply a temperature gradient. For instance, the platinum is hotter than the magnet. Think of YIG again if you want. And then you can drive a thermally excited spin current across this interface. So you again get the spin accumulation, the Magnon accumulation in this magnetic insulator in the green thing. And then again, the magnets can diffuse, and you can detect these thermally generated magnons via the inverse spin Hall effect, so electrically again in this second electrode. And now there's only one spin Hall process involved, and that's why you only see sort of spin Hall effect to the power of 1 or cosine or sine phi, and not the sine square or cosine square phi dependence. And actually, we like to do these spin-Seebeck experiments also using electrical excitation. We just drive large enough currents in this left platinum electrode, and then you get Joule heating. And the Joule heating then generates this thermal gradient. So you can do an all electrical, thermally driven experiment. If you want to see more details, this was first discussed in this APL here. Okay, so essentially, we're all set for the experiments. There is one issue, though, as I tried to illustrate. The orientation of the magnetization is key for this Magnon diffusion process and the detection, generation detection efficiency in the spin using spin Hall physics. In the chromia samples, that is an issue at first glance, because chromia Cr2O3 is an antiferromagnet. So there's two magnetic sublattices, M1 and M2. And they exactly cancel. So there is no net moment, and you can't play seemingly the games that we like to play. And actually, in the thin films that we get from Tobias Kossup, they are grown on sapphire 0001, and that means that the easy axis in the antiferromagnet is along the growth direction, or what I call the Z direction here. And if you think in terms of a spin superfluid, this might be a problem because for a spin superfluid to propagate according to theory, the anisotropy, there should be an easy plane or vanishing anisotropy in the plane perpendicular to transport. So we should have vanishing anisotropy in the XZ plane, and a uniaxial anisotropy along Z does not fulfill that condition. But also Yuan et al. In their chromia platinum samples, they also had samples oriented like ours, and they also saw the spin superfluid, so maybe that is not such a big problem after all. And the way to see spin-Seebeck effect then hinges on counted moments. So you apply an in-plane magnetic field, and if you have an antiferromagnet with this two sublattices as sketched here, this in-plane field will result in a counting. So you get an induced moment along a counted moment along the field, and this moment can then generate spin-Seebeck effect. The other approach, which might be better for spin superfluid, is to use samples in which the easy axis is in the plane along the y-axis here, and then again apply a large magnetic field, go across the spin flop transition to get the counted moment and the spin-Seebeck effect. But then you have this anisotropy free plane perpendicular to the direction of transport. Okay, so now let's look at experiments. This is again the YIG platinum sample I've shown before, just for illustration purposes. I don't have a nice figure of the chromia platinum nanostructures, unfortunately. But we again do these experiments. So we rotate the external magnetic field 2 Tesla in different planes. This is data taken at 10 Kelvin, and I'm now showing the local spin-Seebeck response. We can extract that using sort of a harmonic analysis, just looking at voltages that are even upon current reversal. And this, the top row, is the non-local signal. And what you should take away from this graph is we see this cosine shaped modulation in the two rotation planes where we expect the spin-Seebeck effect to be detectable, and we see nothing in the third plane, and that works for the local and the non-local contacts alike. So you can look at these signals in more detail. There is one interesting feature. So the top panel, this is just one rotation plane. The top panel is the local signal. The bottom panel is this non-local signal. And the color now describes temperature. And you see that if you go from blue to red to gray, the signal strength increases. So the lower the temperature, the larger the spin-Seebeck signal. This holds true for the local and the non-local signal. And this now is with all signs treated correctly, we see a different polarity for the local and non-local spin-Seebeck. Maybe a side note on the quantities on the y-axis. This is commonplace in this non-local business to actually again use a resistance, or a quantity that looks like a resistance, but actually it's just the voltage that you detect divided by the current squared, because you look at these signals that are quadratic in current, Joule heating related. So although this is called resistance, strictly speaking, it's not a resistance, it's resistance divided by current. In any case, what we obtain is that we see these spin-Seebeck type signals. They become prominent only at temperatures of 50 Kelvin and lower, roughly, and they become very large at low temperature. And we can extract the magnitude of this spin-Seebeck signal. So again, top panel is the local, bottom panel is the non-local signal. Here on the top axis is a real temperature scale. This is an inverse temperature scale on the bottom. And you see that both the local spin-Seebeck signal saturates at low temperature, and the non-local does likewise. And this looks surprisingly similar to the results by Yuan et al. So this is data taken from their paper, actually from the supplements. For a 45 nanometer chromia sample, we had 200 nanometers. The contact separation in our case was 0.4 micron. They had 10 micron. But if you look at this inset here, this again is this non-local resistance, so comparable to these data. as a function of inverse temperature. And they also see this saturation at resistance, non-local resistances of the order of 1 volt per amp squared. And we see also this saturation, our non-local resistance is slightly larger, 20-30 volts per amp squared, but we have very much shorter separation between the contacts. So it seems to be the same ballpark, which is very surprising. And then we also try to look at the impact of the driving current, and we see a clear scaling of the non-local spin-Seebeck signal with the driving current. But we see no evidence for a threshold as reported by Yuan and co-workers, who saw a clear threshold behavior which marked the onset of this superconducting or this spin fluid phase. Sorry. So we could not reproduce the threshold. Then we tried to look at the scaling, and this is quite busy. I'm sorry, but I'm trying to give you all possible interpretations. So this is this non-local resistance, again, as a function of the contact separation. The symbols are the data, and these colored lines are the fits. In our view, the best fit that we can obtain to these data, both in a linear or in a log-lin depiction, is actually such an exponential decay. And I tried to illustrate that here. So we fit this exponential decay and obtain a Magnon diffusion length or a length scale L sub m here, which is of the order of 0.5 micron at 3 Kelvin. If you compare again with the superfluid reported by Yuan et al., they saw something which has a more complex, so 1 over this sum type drop-off and a much longer Magnon diffusion length. This is again taken from their paper. They try to fit different power laws, and we again only seem to obtain reasonable agreement with this exponential decay. So also here our results do not are not consistent with what Yuan et al. have found. Okay, so let me wrap up that part. We see a clear spin-Seebeck voltage in the chromium platin, which strangely enough is present only at low temperature. These thermoelectric effects also typically disappear at low temperature. This effect becomes prominent at low temperature, which you might interpret as evidence for this spin superfluid phase. That's why I put the plus here. But the other pieces of evidence that we found do not match with a spin superfluid. So we see this exponential scaling, which you would not expect for the superfluid, a rather short mean free path or diffusion length, and actually the geometry is not appropriate if you trust theory. So I guess what I would conclude from this is that our results are consistent with a spin-Seebeck effect due to magnetization counting, but we have no evidence for this spin superfluid phase. Although I must emphasize that we only looked at small contact separations, so of the order of a micron, and maybe also 2 small drives. And there will be a manuscript on the archive soon with these data if you want to look them up. Okay, so with all these data that I've shown that do not really seem to indicate that magnons play an important role, I thought maybe in the last few minutes I'll show you this what we call scratch test for magnon transport. So I'll hop back to YIG platinum heterostructures. And the drive behind these experiments is a few years old. The group of Barry Zink and other groups worldwide published such non-local transport experiments, so always platinum strips on top of some material, and found non-local signals also for very large contact separations, so tens of microns, and in particular in materials which are paramagnetic, so there's no long-range order, no magnons in principle. And this is very surprising. So we thought it might be worthwhile to really check whether the magnon transport in these YIG platinum heterostructures that really are the Drosophila of these experiments, whether really we can find evidence for magnon transport. And the issue that we had in mind at the time was, well, actually the YIG thin films or the magnetic thin films typically are thin, a few hundred nanometers at most, and they are deposited on very thick substrates, so a couple hundred microns, so 1,000 times thicker substrates. And you could easily envisage other processes where, for instance, the left electrode generates a thermal gradient, phonons, whatever, and then transfers signal to the non-local electrode, and you don't need the magnons at all. So the idea we had was to go for a scratch test in the spirit of Jos Heremans, who did that for SPIN-Seebeck a while ago. So you essentially use a focused ion beam, and you cut a trench into the YIG, and if you do so, the magnons will be confined to this excitation part on the left. So you can really, you should be able to completely suppress the non-local signal if you impede magnons traveling from the left to the right side. Okay, so this is what we did. Now we again use magnon-mediated magnetoresistance in YIG platinum at room temperature, and what I'm showing here is again a simplified top view. So we inject current in the left electrode, we measure the non-local signal in the right electrode, and to actually test whether the YIG platinum structure is working, we also measure the local magnetoresistance response, which we call spin-Hall magnetoresistance. So the top panel is spin-Hall magnetoresistance, and the bottom panel is the non-local signal as a function of the orientation of the external magnetic field. And you see that in the as-patterned structure, we see a clear local and non-local response. And then we inserted this FIP cut. So we removed the YIG in between the two platinum electrodes. And what you see is that the non-local signal completely goes away, whereas the local signal stays. It becomes smaller because we weren't very careful with the FIB gallium beam. So we also looked at the top contacts to know where to cut, and that obviously deteriorates either the platinum or the interface. So the injection efficiency goes down, but it's still active. So we should be able to generate these magnon accumulations, but we can't detect it in the non-local signal. It does not reach the non-local contact. And you can actually zoom in, and to within our experimental resolution here, there is no signal whatsoever. And you can then invert the game and drive current in the right electrode and measure the non-local on the left, and you see the same thing. So also the right, the detection electrode is working, is still spin-Hall active, but we see no non-local signal. So really you can suppress the signal, this magnon transport signal, by cutting the YIG. And you can play games and only cut half, and you see that the signal goes down by about a factor 2, or you try to cut only half of the thickness, so not fully through the YIG, and you see that the signal essentially goes away very quickly. So it's all consistent with magnon transport. Okay, let me wrap up. Before doing that, quickly acknowledge the people who did the work. This is mostly Richard Schlitz and Prasanta Muduli in Dresden. And we had these nice chromia samples from Tobias and Dennis in Rossendorf. And we still benefit from the interaction with my former place, Walter Meissner, and infrastructure at the Leibniz Institute for Solid State and Materials Research. And with that, I'll just flash my outline, and thank you for the attention.